Okay, let's get started. Using Zephyr RTOS for professional audio over IP. My name is Peter. Hello, everyone. I work as a hardware and software developer at Moser Engineering here in Winterthur. I studied electrical engineering, completed my master's degree in information and communication technologies here at ZHAW almost 10 years ago at the Institute for Signal Processing and Wireless Communication. If you have any questions afterwards, please feel free to contact me at my email address. Well, key motivation. A few months ago, I had some time left between two major customer projects, and I set myself the goal to finally get started with Zephyr. My main motivation was the huge ecosystem of drivers, modules, together with a high level of abstraction and a really great community. Our embedded applications are getting more and more complex. Even the simplest devices seem to require file system, connectivity, cloud connection, all those nice things, and of course, in a secure way. Also regarding European Cyber Resiliency Act, of course. But getting started with a new technology can be exhausting. So I try to make it a bit interesting. I picked one of the challenges in one of the current customer projects. And this is about creating a proof of concept, or it's about replacing a module that they are using from a vendor that it does not exist anymore. And the goal was to create at least a proof of concept, whether we could replace this module, implement it ourselves, let's say with reasonable effort. What is it all about? Audio over IP modules are commonly used in professional audio applications like TV, broadcast, studios, live concert events. This is strictly professional application. So streaming like YouTube, Spotify, or internet radio is not part of this topic. These are completely different technologies. Some of the well-known standards are AES-67, or Dante, or AVB, or SEMTE 2110, which are, well, except Dante, all the other ones are actually open standards. One of the most important aspects is the real-time ability. We are talking about delays in the range of 1 to 10 milliseconds, more like in the neighborhood of 1 millisecond. A typical default value would be 2 milliseconds from sender to receiver. There are different solutions are already available on the market. Those modules are quite common in professional audio products. And if you can see, many of them are using FPGAs to meet the strict timing requirements. These modules are usually able to handle multiple channels up to 64 or even more. And of course, you can connect as many modules as you want on a network and distribute hundreds or even thousands of audio channels, all of them always synchronized to each other. So how hard could it be? AES-67 explained in 5 minutes. What technologies are actually used to implement AES-67, an open standard for audio over IP. Our system usually consists of a transmitter and one or many receivers connected over IP infrastructure using multicast. For my implementation, I focused on the receiver end because it's a bit more a bit easier to implement. The inputs and outputs could be digital audio or analog audio, depends on the application. Total latency is measured from the input of the transmitter to the output of the receiver. For AES-67, we basically need 4 key technologies. First of all, time synchronization. Second, some kind of transfer protocol, then a transcription protocol, and some kind of discovery. Those I will explain in the next few slides. Precision time protocol, we already heard it several times today. Compared to NTP, NTP has ever accuracy somewhere in the milliseconds range. PTP, well, it depends. The accuracy goes somewhere from microseconds to nanoseconds, but it does require hardware support. If you're looking for the experts regarding PTP, they're already sitting in the room. As already mentioned, the Institute of Embedded Systems was heavily involved with standardization of PTP since the beginning. And if you're looking for a more practical introduction to PTP, I can highly recommend this year's Computer Chaos Club talk at the conference. If you want to use PTP with Zephyr, I can highly recommend switch to the main branch. I committed a fix regarding the Grandmaster mode. Now this one is working too. Synchronization is done. This already solves many issues. Next is how can we get audio data actually over the network. AES67 is using RTP, real-time transport protocol. It's implemented, it was standardized somewhere in the mid-90s. But it's a really simple protocol. We have a sequence number that solves the out of order issue with a timestamp that is referred to PTP, and there is the raw audio data. But there is no information about how many channels, what sample rate, what coding, just raw audio data. Really efficient, really simple. And Zephyr, in this case, offers the native network API with multicast support and, most importantly, with zero copy. So the third part we need is session description protocol. Fancy name for just a text file that contains the name of the stream, the sample rate, the number of channels, the encoding, IP address of the multicast group, and the MAC address of the PTP Grandmaster it is referring to. Now we're basically done. AES67 already works this way. We can copy the text file from the transmitter to the receiver, and it will work just fine. We could either also open this text file with a VLC media player, and it will immediately start receiving this AES67 audio stream. But, well, in a modern world, we like to have it in a more plug-and-play manner. So discovery and announcement, there are multiple options regarding this topic. SAP is one of the protocols. SAP adds a little header to the SDP file and distributes it over the network once a second. MDNS, or also called Bonjour, well known for discovering printers, can also be used for discovering AES67 devices, also a very simple protocol. In this case, I use the network API over the POSIX standard offered by Zephyr. Well, we are already done. AES67 is explained. This should work. Next part, getting started with Zephyr. First of all, I need some hardware to play with. And of course, this project is mainly for demonstration purpose. I selected the one with the largest display, a color touch display. Most important part. Then we needed Ethernet support with PTP, which is quite common today. To make my life a bit easier, I selected one with great Zephyr support already out of the box. On strong processor because it's fun. A large memory mainly for display buffer. Audio buffers are not that big topic actually, because with the low latency, we work with very small buffers. And we require an audio interface, which we can fine-tune the clock to the PTP source, and preferably the analog to digital analog converter would be nice if it's already included on the board. Well, quick reality check. It's an amazing display, and Zephyr offers amazing driver support regarding graphic displays, LVGL library. It's amazing. The only thing missing was the little configuration file for my display, and it was a rough start to get the device tree working, but I eventually did. Second, yeah, I needed a lot of memory for the display buffers, but the onboard quad SPI memory was not supported. So this took me also quite some time to get my memory initialized. Audio interface. This is a nice story. During my work, I discovered that somebody already implemented an audio driver. It was on the main branch, not yet released, but I was able to use that, and this was really great to have this community support. The codec is still not supported, but just connected a different one. Final proof of concept, it works. I can now receive the session announcement protocol, this little text file. I can parse the text file. I can receive the AES 667 RTP audio stream over multicast. I can synchronize the local audio clock to the PTP clock. And of course, touch and LVGL is working just flawlessly. This was really a joy to implement. The whole solution is running on an STM32H7, and on the full load, including touch and everything, it's somewhere around 7% CPU load, so complete overkill. a lot of room for more audio channels. I'm running on the latest main branch release, 4.3 and whatever is on the branch. Short conclusion. It was a great start for me to get familiar with Zephyr, implement my first project, getting the initial steep learning curve. Zephyr proven to me extremely reliable and stable during the whole project. Maybe some lessons learned. Use main branch if you're on a new hardware, or at least peek on the main branch. What is going on? Each and every week, or at least 100 commits are merged. Also expect that you maybe have to patch a driver or add your custom features. It might be a good idea to maintain your own Zephyr fork on your GitHub, so you are ready to push your changes upstream. And documentation might be a bit fragmented. I can highly recommend to also read the GitHub issues and what the community is doing on the different channels. But overall, well, Zephyr was a great experience for me. I would say for me, it's the perfect fit for modern, scalable, and connected embedded systems. Yeah, thank you very much.